Great. So we were looking at the Rosland approximation. Let's briefly summarize for Nitya's benefit. So Nitya, if there's anything in my summary where, in which you have questions, please stop me. Do not hesitate. Yeah. Okay, so we were looking at various solutions of the radiative transfer equation. But in strictly speaking, we've already solved the radiative transfer problem by writing the radiative transfer equation, which can be solved numerically, or we're using various techniques. But once you cast the equation, then this equation has solutions, and so we can solve any problem in principle. But there are a few cases which are particularly interesting, where we have analytical solutions or approximate solutions. Okay, so the first case is the uniform slab, where I've extended at I've expanded at length here. This is something in this formula you have to know by heart, equation 40. We then looked at what happens in a very optically thick medium. So in a very optically thick medium, photons can undergo a random walk, a scattering random walk, which is terminated by a real absorption. We are imagining here that the interaction of photon and matter can be described by two terms, an absorption term and a scattering term, okay, which would be the continuum description. And in each encounter between the photon and matter, there can be a scattering event or an absorption event. And so in this description of the random walk, we have, which here I think I'm following Rybicki and Lightman, we see that the probability for absorption in each step is given by this epsilon ratio, which is the ratio of the pure absorption coefficient divided by the total absorption coefficient, including the scattering absorption coefficient. And so we saw that in a random walk, the random walk is going to be terminated by when we have an absorption, and if you have the probability of absorption is given by 40 by this equation, and we imagine this is less than 1, then we have a unit probability of absorption for some number of steps n. So we equate n times epsilon equals 1, and so the average number of steps before absorption is 1 over epsilon. Okay, so that's the number of steps. And in a random walk, the net displacement is given by the square root of n times the size of the displacement. Okay, so the net displacement until absorption is given by this expression. So that's the displacement in terms of the step size, and divided by the square root of this quantity epsilon. Epsilon is 1 minus the albedo. You might have heard of the albedo before. Here I'm using this notation. I'm talking about the displacement as in terms of the dispersion of the real displacement. The R would be the amplitude of the position vector of a photon after n steps, n here. Okay. But I'm talking about the dispersion because we are discussing statistics here. I mean, this is a random process, and so I'm using the dispersion to describe the displacement of the photon. Okay, so this is what Rybicki and Lightman call L star. I think I prefer using the dispersion, which is what it is. But it's just a matter of notation. And so if we have a medium that's much larger than this displacement, which is also called the thermalization length, then the medium is said to be effectively thick, as in physically thick, not just optically thick. It's also optically thick. Okay, so the medium will be indeed absorbed inside the medium. The photons will be absorbed in the medium. Okay, so all this is important to introduce this idea of thermalization length, where we have the possibility to introduce local thermodynamical equilibrium. So if the medium is effectively optically thick, it's effectively thickened, then the photons cannot escape and they cannot cool the medium efficiently. The medium can only cool by the surface. So deep inside the medium, we have a chance to establish some sort of steady state where photons are trapped, and any emitted photon will be absorbed locally. So energy can be conserved, and no energy is lost in first order, in first approximation, because of course there are there are boundary effects. But if we're deep inside the medium, there is a chance that energy is conserved, and we might have steady state. In addition, since the medium is effectively thick, it is also optically thick, and the radiation intensity approaches the source function. In the case of thermal processes, this is the Planck function. And so we introduce a local temperature, which is the LTE approximation. Okay, so we have this idea that we are inside the medium. Oops. Okay, so we are deep inside a star, and well, we have a blob here, and so that blob is at some position vector x, and we have a temperature at the position x. Okay, so this is called local thermodynamic equilibrium. That can happen if the medium is effectively thick. We then introduced the Rossellin approximation, which is going to give us an estimate of a way to connect the transport of energy, the radiation flux, with the gradient in this temperature field. Okay, so the idea is that we have so that could be deep inside the stellar interior. We have some temperature at this position x1. Okay, and that could be that the size of this blob here would be sigma of r, if you want. So this is called L star in Rayleigh-Leibniz notation. And then we could have a neighboring blob, same size, at x2. Okay, and we have that the temperature at x2 is less than the temperature of x1. Okay, we deep inside the stellar interior, we have the thermonuclear furnace, and in the surface we have the photosphere, which is at around 6,000 Kelvin. Okay, and in the interior we are at 100 million Kelvin. Okay, so that surely there is a gradient in temperature, and neighboring blobs, which are separated by this thermalization length, will have a temperature which is similar because they're nearby, but not exactly identical. There is a tiny difference. Okay. So if there is a difference in local temperature, it means that the specific intensity field at this position, whatever position, is approximately the Planck function. Okay. It's not quite the Planck function. It's not exactly the Planck function. It's very close to it, but it cannot be exactly the Planck function, because if it were, then everything would be in thermodynamic equilibrium, which means that the temperature is constant everywhere. Okay, thermal equilibrium requires equality of the temperatures. Okay, this is a condition for thermodynamic equilibrium to occur. We have mechanical equilibrium requires the equality of pressure. Thermal equilibrium requires the equality of the temperatures. Chemical equilibrium requires equality of the chemical potential, and so on. So thermodynamic equilibrium really needs flat temperature profile. If you do not have a flat temperature profile, such as the case is the case in a star, it means that you do not have a strict equilibrium. You might be close to it, but not exactly. So this is called LTE. Okay. And so the idea is that the deviations from the Planck functions are very small, and we introduce them. We look at what those perturbations are like. We consider those deviations from the Planck law using the radiative transfer equation. So this derivation here follows what's described in Rybig and Lightman. Today I'll show an alternative derivation, but let's follow this one for now, which is what we did last week. This is the standard transfer equation, equation 42. Okay, it's in the case of isotropic scattering. Okay, so this is okay for isotropic scattering, where we factorized alpha scat here from I nu. Yes, and so we're looking at array in some direction given by unit vector S, okay? And we group together the absorption and scattering coefficients inside this single absorption coefficient alpha nu. So if we can rewrite equation 42 as equation 43 here, and you know, like so we replace this total derivative by the partial derivative, and solve for I nu. So we have I nu is close to the source function, which is the Planck function, but there is this small perturbation term, okay? And this perturbation term then is connected with the gradient of the specific intensity field. And so here we are going to make the Rosseland approximation, which means we're going to replace I nu by the source function, B nu, leading to equation 44. So this is the core of the Rosseland approximation, okay? So this is a rewrite of the radiative transfer equation, except that we have replaced the dependency in I nu here on the right-hand side, because we assume I nu is close to Planck's function. So whatever this is small, okay? So making a small error on this small thing should be okay. And this is what we've reached, where we have an expression for the specific intensity field, which depends on local conditions only, meaning the local temperature and its gradient through the Planck function. So if we want to obtain the flux, then we integrate over a direction, okay? So this notation here might be somewhat confusing. I'll clarify this now. We have, so the flux vector, then I write as an integral of the specific intensity field over direction, okay? So if we have, for instance, F nu dot z, well, that would be as F nu z, so the vertical direction, okay? But this is going to be the integral of I nu k dot z times d omega. And this one, of course, is cos theta, okay? And this one here is sine theta d theta. Right? Okay, so this is what we mean with this vectorial flux. Okay. Oh well, I had already expanded this in the transparency. I hadn't noticed. But anyway, so this is double clear then. We then connect this partial derivative with the gradient. So this is so this basically what we mean with this partial derivative in the direction of a ray along the ray, which is just direction s, is this really. That's a shorthand for this expression, which is the gradient of being of whatever quantity being in this case projected along the direction of the ray. That's what we mean by this partial derivative. Now we can connect this with a gradient along one of the Cartesian directions in the plane parallel geometry. Okay, we will be looking shortly at an alternative to this description, not using the plane parallel geometry. Yes, I mean, so we saw, last time that this is indeed the case. We have this is z direction, this is s, okay, and that would be theta, and we have here mu equals cosine theta. Okay, so if I look at an element here along ds, okay, we have that sorry, ds is dz divided by cosine theta. Okay, and so that's how we get to this expression here. Nitia, is that clear? Do you want me to expand further on this? Okay.
This is clear for me.
Okay. And so we integrate equation 44, which is this Rosenland approximation. Basically, we do. Let me write equation 44. We say I nu is about b nu 1 over alpha nu times. Okay, and then oops, and where was I? Okay, yes. So we integrate equation 44. Yes, we calculate this basically. So let me add another sheet. And so we integrate. So this is k nu dot z times I nu is equal to the integral of k nu dot z times, well, what was on the right hand side, okay. And this thing here is going to be f nu in the direction z. And we looked at these terms on the right hand side last time, it was on last Thursday. Okay, we saw that the first term is going to be 0, and that the second term is minus 4 pi divided by 3 alpha nu dv nu over dz. Okay, so this is the development of this equation I did last time. It's recorded and it's online. So in case there were issues there, you can go back and look at the video. It's also expanded in the textbook. Okay, but the interesting thing here is that now we have an expression for the flux of radiation in the direction z in terms of the gradient of the Planck function over the direction z. So why does the Planck function change with z bar? Because this is the Planck function here depends on the local temperature. Okay, so we are now starting new material, which is looking at this Rosson approximation again, but from a more general perspective. First, we remember the moments of the specific intensity field. We have the zero moment of the specific intensity field is also called the mean specific intensity, and we saw this is connected with local energy density. That would be the moment zero. Moment one is then weighted by the direction k. So remember that kz would be cos theta, kx would be sine theta, sine phi, etc. Sorry. The last one is the second moment. This is radiation pressure tensor. It's a matrix, which is written like that. It's kind of confusing at first. Sorry. So let me write an example. We have so this is C P nu ij with this is the two indexes. It's a matrix which is given by ki over kj times the specific intensity field. Okay, so for instance, if we have kz, kx, that would be sorry, cos theta times sine theta, cos phi, etc. Okay, so it is a matrix, and then we go back to the radiative transfer equation. So this is the same radiative transfer equation, but this time I'm not using isotropic scattering. I'm just writing out the RT equation in full using the phase function. So this is a more general case than the previous one we just looked at. This should not be new. I mean, this form of the radiative transfer equation is the one you'll meet now in 2021. Everyone knows what the phase function is. Once you talk about scattering, there is a phase function, and you do not restrict yourself to only isotropic scattering. So this is the full form of the radiative transfer equation in steady state, no time dependence. The idea then is to calculate the first moment of this equation. So we multiply by k and integrate over solid angles. Now here, this is and what follows is a bit tricky. First, notice the first term here on the left. So we, for the first term, on the left-hand side, we integrate over solid angle and multiply by the direction k. And what do we apply this to? It's k dot gradient of I nu. Okay. Now, this gradient applies on the x coordinates. Okay, so that thing here is basically the partial derivative over the position x. And this is the only quantity here that might depend on the position x. These are angular integrations. Okay, so this gradient here can go outside. We can revert this. We can simply write this as the integral, closed integral over d omega times the gradient. I'm gonna do one more step here. K times nabla dot k I nu. So if you want to convince yourselves of this, you can spell it out. You can say, well, this is the partial derivative along x times kx I nu plus the partial derivative along y and ky I nu plus partial derivative along z kz I nu. And then you say, well, does kx depend on x? I mean, it doesn't, because kx is, well, we saw it, it's sine theta and cos phi, okay? And it doesn't depend on the position where we are evaluating the specific intensity field. So basically, we have this is the situation. We have this position vector x, and we have at position vector x. What happened? Uh-oh. Are you there? Okay.
Yeah.
What's wrong with my
What? Yes, we're here.
Apparently it's failing. This has happened before. What's going on here? Let's see. I'll reset the Wacom. It's not working. Okay. Let's see. Okay, it's back online. So, and here we have, at this position, we have this angular coordinates, where we have then this direction vector k, which then has got this angle theta, phi, and so on. And so these direction vectors here are indeed x, y, and z, but you can see that this theta and phi parameters are independent. They do not depend on the position vector x. Okay, so for any position vector x, I perform the angular integration, and when I do the angular integration, I do not change x. Okay, so going back here, we have then that the dx times kx I new is the same as kx times dx I new. See, I can take it out of the derivative. So that's why I put k dot nabla equals to nabla dot k. Okay, this is a trick not easy to follow, but because it's confusing because you know I'm performing a derivative over x, and I've got the x component of this unit vector, but this unit vector kx is just the x coordinate of the direction k, which is sine theta and cos theta plus phi, which do not depend on where I'm placing or derivating the origin, which is the position of where I'm evaluating the specific intensity field. Okay, so I can perform this change here. I mean, the partial derivative of kx I new is the same as kx times dx I new. Okay. Is that clear to everyone? In this case, it's not easy to follow, but I hope you see the logic of it. And then I do the same trick again, because this vector here, and that's even worse, I think. But let's try to see how it goes. We have the integral of then d omega times ki. So here I've got some I component of this. This is the vector I'm rewriting in terms of its component, right? So that would be times the divergence of this quantity here. Okay, so I can easily absorb this ki into the divergence again. I can rewrite this as just this term. This thing here is going to be nabla dot k times ki I new, with the same argument that this direction of I mean this angular direction does not depend on the gradient of the of where I'm evaluating the specific intensity field.
Professor?
Yes.
So ki, it means that now there's 3 equations?
Yes.
One for x, one for y, and one for z?
Yes.
Okay.
We have that. Thank you very much, Felipe, for the question. I wasn't precise enough on that aspect. Look at what we're doing. We have one equation, which is the equation of radiative transfer here, 49. I am multiplying 49 by this direction k and integrating. Okay. But this one has got 3. It's a vector, so there's 3 equations. Okay, so this is like striking 3 equations out of 1. Okay, each of these ones is the integral over solid angle times ki. Another one is integral over solid angle times kj and kk, and so on. Okay, so yes, there's 3 equations, and so in the end, we have that this term in sine is then going to be the integral over sine angle of nabla dot k I new. And again, this nabla factor gradient does not depend on the direction of integration. This variable integration variable is of a direction, and this one derivates the position vector. So this is the same as I was explaining here. The angular iteration is performed over theta and phi, and we do not change x. Okay, We can factor out the gradient and write it down as ki times k I nu. And this is basically what we have here on the left-hand side. Now, what's the trickiest part? Okay, now the right-hand side is not so difficult. The first term, the integral over d omega times ki j nu. So, for instance, time kz, just to focus on some direction. Okay, so that's going to be a constant. Okay, and so we are evaluating the integral of the d omega over of cos theta, and that is 0. And we have the same problem for all other coordinates x and y. Okay, so the first term here is 0. For the same reasons, this last term, the scattering term, is also 0 because of this angular part here. Because this is this function k is even. Sorry, it's no, that's odd, and this one is even. So the product is odd, and when you integrate, it gives you 0. Okay, so what I'm trying to say is that the integral of the omega times some direction, well, cos theta is a good example, times phi k prime. This thing here is going to be 0 because this is even, so that we have two. It's not so easy to explain this one. Let me. We have yeah, well, okay, we have some direction k prime here, and what I'm trying to say is that yes, this is the same as phi of minus k into k prime. So we have this situation. No, I think that this is not what I meant. It's not going to work like that. I forgot why it's obviously 0. Let me see if I can remember quickly. I think Nitya, you have a class at 10. Do you have a lecture at 10, Nitya, or can I go on a bit more?
Yes, Professor, I have class at 10.
Oh, okay. So I got to wrap up. Started late, but this I'm trying to remember why is this last term 0. So let's see if we have cos theta here. Let's write it down. This is going to be for some direction k prime. This is going to be yes, so d phi times sin theta. Oh, okay. So yes, so okay. It's simple. It's so let's group the theta part. Just the theta part. Plus theta, and then I'm integrating over this phi variable times phi, which is a phase function. It's k over k prime. So that part here, this one is basically the integral over 0 to 2 pi of d phi times the phase function, which is going to depend on this direction phi, some direction theta, and the reference direction phi prime and theta prime. So these ones do not change in this integral. Okay. Yes. And okay, I forgot. I don't remember. I don't remember why this is 0. I think we'll have to leave it for Thursday because I'm past the hour. So I'll just refresh my memory as to why this is obviously 0. It seemed obvious when I wrote it down. I can't remember now. Surely there must be a simple explanation, which I'm not seeing at the moment. So sorry for starting late, and we'll meet on Thursday then. Ciao.
So goodbye.
Bye.